Welcome to my talk about automatic machine learning. My name is Andreas Mueller at the Columbia Data Science Institute. I'm a co-developer of the machine learning library SKlearn. So I want to talk to you about today what automatic machine learning is, why we want it, and what the recent developments are. None of what I'm going to talk about is really my work, but I hope I can give you a good overview of what's been happening in the area. So first off, why do we want automatic machine learning? My personal goal is to make machine learning accessible and easy to use for everybody. Ideally, you shouldn't need to read a book or understand the library or have a strong math background to apply machine learning to a problem. Simply, that's not the case right now. And to apply machine learning successfully, you need to have a significant amount of knowledge in the field. To start with, let me talk about where we are right now, in particular with respect to SKlearn, which is arguably the default machine learning library, at least in Python. So what are the issues that beginners face, and how can we improve upon them? I said none of this is my work, by which I meant none of the solutions is my work. So the problems might very well be somewhat my work. So I'm not sure if you've seen this. At some point, I made this ridiculous flowchart here. The idea was that it walks you through which machine learning model to pick for which particular task. It was a bit meant as a joke because applying machine learning is much more complex than what the chart suggests. Still, people found it quite useful because it gave them at least some guidance and some starting point on what kind of model to use. SKlearn has an extensive user guide, but it doesn't really give you a lot of advice on where to start. As a beginner, it's therefore hard to know which models to try first and which models might be appropriate for a given task. Moreover, once you selected the model, you also need to select hyperparameters. Most machine learning models have some parameters to tune to get the best performance. SKlearn models usually have many options, not all of which actually change the outcome. Many of them are trade-offs between runtime and accuracy, or very specific use cases. And it's hard for a newcomer to know which of these are to tune. Even if you know which parameters are important, you might still not know what are good ranges for the values, or how many values you should try, and whether you should try them on, like, say, a linear or logarithmic scale. The same is true if you're not using SKlearn, but for example, a deep learning library. Selecting and configuring a neural network can be quite challenging. The final issue with the current situation, at least in Python, is that SKlearn really likes to be very explicit. There's very little magic in the background, and you need to manually specify each data processing step. That's a bit different in some R libraries, but SKlearn Python gives the user a little bit more control. That means, however, that you have to take care of many things yourself. For example, dealing with categorical variables, with missing values, and with scaling the data. So to apply a support vector machine to a data set, you probably shouldn't probably just fit the SVM model. Depending on what kind of data you have, you might want to use something like a one-hot encoder for the categorical variables, an imputer for the missing values, and the standard scaler to standardize the data, each of which has some additional parameters that you need to specify. So beginners often don't know and might get bad results as a consequence. So this is sort of what's less than ideal right now. So what would I like a solution to be? Ideal interface. Import the automatic classifier, and when you fit it, it will provide you with a sequence of more and more accurate models over time, and you can stop at any point. Actually, there's a library called SKlearn, which contains an auto classifier. It does something quite similar. It's not entirely where I'd like it to be, though, and I want to talk about this a little bit more in detail later. But so the idea here is you should not really need to make any manual specification of what models and what hyperparameters to tune. You just say, please train a classifier, and then the algorithms do the rest for you. Good. So that means doing all the pre-processing, all the feature selection, whatever you want. So now that we know where we want to go, what are the steps that we need to take for this? Step 1 for me is to automate the parameter selection. Given a particular model, I want my library to know which parameters are important, how they influence runtime and accuracy, and then search for the best parameter setting on my data set in some smart way. For example, for a support vector machine, that could be the kernel, the parameters for the kernel, and the regularization. For a neural network, it could be the number of layers, the nonlinearities, and the number of units per layer. And, for example, the optimization algorithm. The second step is not only search the space of all the parameters, but also have a candidate list of models and pick out the best model together with the best parameters. So now you not only search over the different neural networks, you search over neural networks and random forests and SVMs and so on. This is sometimes called the cache problem, or combined algorithm selection and hyperparameter optimization. You could even go one step further and ask the library that it knows which model might be good for a particular data set. And we'll talk about that in a little bit. Wait, what is the problem called? Is that cache? But basically, you can also just say automatic model selection. So once we have automatic model selection, what we want is also select the pre-processing steps that the model might need. So you want to automatically select the whole pipeline. So now you have scaling, model missing value imputation, pre-processing of categorical and text variables, and so on. Everything solved automatically. So how can we implement these 3 steps? How do we automate the parameter, model, and pipeline selection? So these are basically very large search problems. You need to search over parameters, models, and pipelines. And so let's look into what goes into doing this search in a smart way. So first of all, we need to formalize our search space. Even if we just want to select the parameters of one particular model, this search space might be quite complex. There's often a mixture of discrete and continuous parameters, such as the kernel of a support vector machine and the regularization. So the kernel would be discrete, the regularization continuous. There's different ways to deal with continuous and discrete parameters, but that also depends a lot on which kind of search strategy you want to use. Another difficulty is that also arises even just for a single model is the existence of conditional parameters. For example, for a neural network, the number of units in the second layer only matters if we actually have at least 2 layers. So whether the number of units in a particular layer matters depends on the other parameter, which says how many layers are there. So the existence of one parameter is conditioned on the existence or on the setting of a different parameter. If we want to search over the whole pipeline, there is another difficulty, which is searching over the structure of the pipeline. Do we want fixed pipelines or pipelines of a fixed length? So for example, we always want some pre-processing, imputation, and scaling, or do we want to create arbitrary graphs? Do we want linear pipelines or anything possible? And these decisions are all important, and again, they influence what kind of search strategy we can use. And finally, there's also the question what to include in the search space. Should we include all models that we know? Should we include like all of SKlearn or all of R and all possible parameters? Or should we trim it down and only look at the most important ones, or the ones that we know are performing best? So once we thought about the search space and how to specify it, we then need to think about what kind of search method we want to apply. So the simplest search method you can think of probably is exhaustive search, or often called grid search in this context. So grid search just means you give it a list or an exhaustive combination of all possible parameters and try all of them sequentially, usually. The good thing about this is that it's easy to implement, it's easy to understand, and it's also embarrassingly parallel. So you can just run the search on as many machines as you want in parallel. It's easy to deal with conditional parameters if you specify them correctly, but usually you need to discretize all continuous parameters, and you need to specify explicit lists of parameters to try. Also, you can't naturally trade off accuracy and computational complexity in a grid search. If you specify a grid, you basically need to wait until the end before you get a reasonable result. If you just search half the space, that might not be a good idea to stop them. Also, if you have very many parameters, the search space grows exponentially. So with many parameters, for example, if you want to build a complex pipeline with many steps, exhaustive search quickly becomes unfeasible. So another relatively straightforward method is the randomized search, which randomly samples the parameters for each model from a user's specified probability distribution. So randomized search can deal with conditional parameters, and again, it's just embarrassingly parallel. You can just randomly sample on as many machines as you want, completely independently. It can naturally deal with continuous variables by using continuous distributions. And depending on how you pick these, you can also, and you can either sort of use the continuous distributions, or you can discretize continuous distributions. And you can specify any kind of prior distribution that you want. In contrast to grid search, if you do randomized search, you can stop at any point, because the randomized search explores the whole space, well, at random. If you do 100 steps, you can look at the results, and you can do 100 more steps or 1,000 more steps. And each point, you have something like a valid result. So this is known as an anytime algorithm, which is something that I really want. Another cool thing about randomized search is that for continuous distributions, the results will likely to be much better than grid search if you give it the same amount of computation. That's because we're not using any regular structure to find the evaluation points. If some of the parameters are less important, grid search spends a lot of redundant computation on exploring these unimportant points, and randomized search actually doesn't care about it at all. If you add unimportant parameters to randomized search, it doesn't change the speed at all. I'll link to a paper at the end, and that gives more details about this. It's really cool. But still, randomized search is still pretty stupid. You don't learn from your search at all. You just try out many, many points. And so there's another family of much more sophisticated methods called Bayesian optimization, or sequential model-based optimization, or SMBO for short. These are basically methods for global optimization of any expensive-to-compute arbitrary function, such as the validation accuracy of a machine learning model. Difference to other optimization algorithms that you might be familiar with, like gradient descent or LBFGS, is that Bayesian optimization usually doesn't rely on gradients, because for searching hyperparameters, you usually don't have gradients available, so you need a gradient-free algorithm. Also, they're optimized to deal with very slow functions, such as learning a neural network. If evaluating your function takes days, you should spend much more effort in finding the next test point than a simpler algorithm would do. So you want to get as much information out of each point that you try as possible. The idea behind all of the SMBO models is to build the probabilistic model of the mapping from a parameter value to the validation set accuracy for a particular model with a particular set of parameters. We iteratively select a model or with the most promising parameters, and build a model with these parameters to evaluate it. So let me walk through this in a little bit more detail. Here's an example of what this might look like when you use a Gaussian process for probabilistic modeling. This is a toy example with a single parameter. There's 6 steps of the algorithm here, and the x-axis is a single parameter we want to tune. Let's say it's a continuous parameter. And the y-axis is the error achieved with this parameter setting, so the mean validation accuracy, for example. In the top row, you can see as a red line the true dependency of the error on the parameters. We want to find the minimum of this red function without access to the function or its gradient. The red dots are observations, so parameter values that we tried and for which we know the validation error we can achieve. We start by picking the first point randomly in n equal 1 on the left-hand side. Then we build the model using this parameter setting and evaluate it. And we get some validation accuracy. That's the height on the y-axis of this point. Then we use this point to build a surrogate model of the red function using, in this case, a Gaussian process. Here you can see this in purple with a mean and standard deviation. So on the left, this model is very bad because we only have a single data point to go off. Now we can use this right now very flat surrogate model to pick a new point to evaluate. We want to find a point that will give a low value of the function we want to optimize, but we also want a point that will provide us with as many new information as possible. This is an instance of what's known as exploration-exploitation trade-off. So we want to pick a good point that's also informative. One possible strategy for this is called lower confidence bound. So this is a strategy to find the next best point to try. You can see the outcome of this strategy in the lower plot. The way this works is we select the lowest point according to one standard deviation around the mean. So basically, the lower plot shows the lower line of the purple function. So the lower contour of the purple function, the lowest one standard deviation. The minimum here is on the very right corner. So the next thing we do is we pick this very right hand corner as the next parameter setting to try. So now we build a model with this hyperparameter setting, we compute the cross-validation accuracy, and then we move to the next panel. So the next panel, we have two red points. One is at the very right. And now we update the purple model. So we rebuild the Gaussian process with these 2 points. And so we get a new estimate of the mean of the function and the standard deviation. So we have a new purple function. Now again, we use the lower confident bound to find the next point to try, and so on. So we minimize the function at the bottom, in the bottom panel, get the next red point, and so on we iterate. And over time, we get closer and closer to the optimum, and we get a model that's very close around the optimum. So if you look at the very right-hand side, the purple function matches the red function very well around the optimum. It doesn't match the red function very well in the other regions, but it doesn't really matter because we're only interested in finding the minimum of the red function. So the key idea here is that in practice, evaluating the red function could mean training a neural network. And so it's very expensive. So we want to try out as few parameter settings as possible. However, evaluating the purple function, our model, or the green function, which is called the acquisition function, is very easy. So this is just a very small machine learning model that we can easily evaluate. It's just predicting with the Gaussian process. We often also have gradients for this. So we have a gradient on the green function, which we didn't have on the red function. So we can build the purple function, which approximates the red function, and then try to optimize the purple function with trying out more points and using a better optimizer. This might be like a little bit much to walk through in like 2 minutes, but I hope I could give you like a general idea. So there's multiple different models you could use. So this one here used the Gaussian process. There are just 3 that I want to mention here. The Gaussian process, which is probably the most commonly used one. There's random forest-based models, also known as SMAC, if you want to use it for Bayesian optimization. And there's a family of non-parametric models called TPE, or tree-structured Parsons window estimate. So These all have different pros and cons. So Gaussian processes are very good at dealing with continuous parameters, but not as good as dealing with discrete parameters. The random forest-based methods and the TPE deal very well with both discrete and continuous parameters. The random forest-based models are also very scalable, while Gaussian processes tend to slow down if you have lots and lots of data points, if you do lots and lots of runs of your model. Then for conditional parameters, which happen a lot if you build more complex pipelines, but as I said, they happen even if you just want to tune a neural network. That's kind of tricky to do with Gaussian processes. But it's very natural both in the TPE and in random forests. However, the Gaussian processes are sort of a standard model for model-based optimization, and there's lots of implementations out there and lots of papers. For the random forest, there's like, I think, 1 or 2 groups working on this, and it seems very promising, but there's not as much research. While for the non-parametric method, that was specifically designed to deal with conditional parameters, but I'm not sure if anyone is still doing research with this a lot. Finally, they also differ a little bit in how you specify the parameters. For Gaussian processes, which mostly works with continuous parameters, you only need to specify an upper and lower bound, where for random forest and non-parametric methods, similar as for randomized search, you need to specify a prior distribution, which might sometimes be tricky. So I'll show you a little bit of a quantitative comparison later. But before we go into the comparison, I want to talk about a couple more methods that can help us implement sort of automatic pipeline selection. So far, we just talked about searching a space of all models that's sort of complicated, structured, and possibly exponentially big. But so that's not really how humans would approach this. As human data scientists, I don't just start randomly trying out all possible models and randomly combining pipelines. I have some intuition about what works, given my previous experience. And this brings us to meta-learning. Meta-learning basically is applying machine learning to automated model selection. So now I want to not always start the search from scratch, but I want to learn from past experience what model should work well on which data set. So it's machine learning applied to machine learning, therefore meta-learning. So the idea of meta-learning is the following. We start with some data set and run our pipeline optimization algorithm. So we specified our search space, and we run like a Gaussian process-based or random forest-based optimization algorithm. This finds a good algorithm and parameter settings for us. So this search usually takes quite a while because the search space is so big. So then we do this again for another data set. We run our optimization again. We get another algorithm and parameters that work well on data set 2. Then we do this again for data set 3 and so on. So we do this for many, many data sets. And this might be quite costly. But once we have a good parameter setting, we can use this setting to train a machine learning model. This is the meta model. It tells us which algorithms are promising on a new data set. To learn this model, we need to represent each data set using what is called meta features. And so now, in this meta model, each data set becomes a data point, and each data set is represented with a feature vector. And the output that we want to predict is the algorithm configuration and parameters that work well on this data set. Then, if someone gives us a new data set, we can compute the meta features. We apply the machine learning meta model that we have, and we'll yield a good algorithm setting with good parameters. So now we don't have to run our expensive search anymore. We can just apply the machine learning model, and it will give us good parameters and a pipeline configuration. At least that's the idea. In practice, what people often do is they use the prediction of this meta-learning model as a starting point for the search. But at least this is much better than starting from scratch every time. Here, we're now able to generalize our knowledge about what works well in machine learning across different data sets. Also, there was a question, so why is it costly? So running the optimization is costly because you have to build many, many models. So let's say you have a neural network and you want to train, you want to tune like the number of layers and the number of nodes in every layer and the nonlinearities. And so let's say this gives you, say, 1,000 combinations for different possible parameter setting, or 10,000 combinations if you try all possible combinations. And that means you need to try out on the order of hundreds or thousands of neural networks that you need to train, which could take weeks before you get a good parameter setting. If you have a model that can predict this, you just need to compute the meta features, and you don't need to do this giant search anymore. Okay, maybe, so the cost was in terms of computation, which is, I guess, the same as AWS cost. It's not costly in terms of human resources. But maybe it's too much computation that you want to do it over and over again. If you can shortcut it, that's better. Okay, I think I'm going to move on, and we can do more questions at the end. So the simplest idea of these meta features is, for example, number of samples in the data set, the number of features in the data set, how sparse the data set is, missing features, presence of categorical variables, something like that. You can also do higher order statistics of the data set, or mutual information between features and labels. One thing that's very often used is so-called landmark features, which basically says, apply a simple model to the algorithm and see how well the simple model does. For example, you can run a decision stump or a naive Bayes model, and computing these models is basically as computationally intensive than computing the mean. So you can just build this machine learning model basically for free, and seeing how good a particular simple model does is a possible input feature to the method learning model. After talking about how to approach the problem of automatic machine learning in general, I want to give you a brief overview of the systems that try to solve this task. And so I'm focusing here more on available open source systems. I'm not really talking so much about commercial applications, which there are also, but it's often unclear what they do. And I'm also not talking about like state-of-the-art research, because there's a lot of papers in this area right now, but there's very few actually implementations that are sort of general purpose. So I want to talk about these more general purpose implementations that are open source. So somewhat unsurprisingly, my favorite of the existing project is a project called SKlearn, which attempts to automate scikit-learn pipelines. It's developed by a group in Freiburg, and you can get it on GitHub and try it out. It uses a fixed setup for the pipeline with, I think, 4 steps, which are imputation, one-hot encoding, feature selection, and scaling, and then a classifier. Wait, that's 5 steps. Wait, okay, it's 5, I guess. It uses method learning, uses a nearest neighbor classifier, and uses that to warm start the search. For the optimization, it uses SMBO, or Bayesian optimization, using SMEC, which is the random forest-based approach that also people from this lab developed. And this package includes a list of, so it also includes a search space. So it includes distribution over the parameters of many of the scikit-learn models to search over. And so they have hand-tuned parameter spaces to search, which means you can basically, they have this auto-classifier and you can run it. For me right now, it's a little bit too complex to set up and it's a little bit too slow, but I mean, I think this is the best that's out there right now. There's also AutoWeka, which is a plugin for Weka that does model and parameter search. It allows you to use both SMAC and TPE. It doesn't do meta-learning, so it does an independent search for each new model. And it doesn't do complex pipelines, it just searches for one model. And I'm not really a Java person, so I don't have a lot of experience with it. That's actually, I think, one of the older packages. There's also HyperOn SKlearn, which is a project by the creator of TPE, James Bergstra, which basically provides a list of parameter settings for many of the scikit-learn models. So again, this defines a search space. And then the search space is optimized with TPE. This also, again, doesn't build pipelines, and it doesn't do meta-learning. And unfortunately, I think this project is no longer maintained. There's another project called TPOT that works quite differently. It's done by my friend Randy Olson, who you probably follow on Twitter. Check it, you probably do. So this uses genetic programming. So it doesn't use the SMBO, the Bayesian optimization that I described, but uses genetic programming to evolve arbitrary complex pipelines of scikit-learn models and arbitrary functions. It contains dictionaries and parameter values to try, but it's like very, very flexible in how everything can be put together. I haven't really seen a benchmark of this against the other methods, but I think Randy's working on that. So these are sort of models that at least try to solve the auto machine learning problem, and either they build pipelines or they just select single models together with parameters. I also want to talk about some of the packages that just do the search. So these are, I call SMU packages that basically optimize arbitrary black box functions. So they don't know anything about models, for example. They don't know what are good parameters to try, but they can do the search for you. Experiment is a particular implementation of Gaussian processes. It came out of a research lab and was quite widely adopted. It implements a lot of pretty advanced research papers, but I think it's not really actively maintained any longer. If you're looking into doing Gaussian process-based optimization, you probably want to look into the next one, which is called GPIOPT. This is another package using Gaussian processes for Bayesian optimization. It comes from Neil Lawrence group that also do GPI, and is really good. And there's Scikit Optimize, which is done by a couple of the scikit-learn people, and some more. It's a relatively fast-moving community project right now and tries to implement a bunch of these algorithms. It has GP-based methods, tree-based methods, and it has like some drop-in replacement for grid search CV and scikit-learn. So I think we don't have that much time anymore, so I'm going to breeze over some of the benchmarks. So here's one particular comparison that I think is interesting, which compares SMAC, TPE, not doing any fancy search, which is called RF baseline. So this is 4 different machine learning problems and optimizing to parameters with different libraries. RF baseline is just using a random forest, and the other one are basically meta-learning packages. And you can see that so there's random search, SMAC, and TPE, which are all doing like fairly well. So lower is better here. This shows average rank of the different models. So after a particular time, which is the best model, which is the second best model, and so on. And so what's interesting here is that the green curve doing random search is not that bad, not that much worse than all the other models. And what's even more interesting is basically if you run the random search on twice the speed, which is then it's actually better than most of the models. So if you just buy twice as much computation, you basically are better than any of the like research methods. So that's kind of quite striking. You can just scale randomized search that easily. Maybe that's a good thing to try. Okay, so there's a couple of things that we've seen that people already do. Sorry, I'm kind of running out of time, but so one thing that I want to do in the future is more cleanly separate the modeling of the search space, the pipeline optimization, the optimization method on the meta learning, and build good solutions for each of them. We have pretty good solutions for optimization methods, but there's very little research on the other ones. Also, most of the methods don't exploit prior knowledge very well. And most methods also, at least the ones that sort of have nice implementations, don't take runtime into consideration. There's some research work on that. So I want to briefly go through some. Yes, Randomized Search X2 is basically you just allow it to run 2 evaluations. And yeah, it's basically running it at twice the speed. All right, so there's a couple of criticisms on doing automatic ML that I want to go through. So one is, well, randomized search actually works very well. It's a criticism of a lot of the SMBO work. As I just showed you, maybe it's better to just buy twice as much computational resources than try to do something fancy. In particular, because randomized search is very easily parallelizable. Another possible criticism is that it's not clear whether we really need to try out 100 different classifiers or very complex pipelines. People have found that, for example, gradient boosting often works very well. And just using a random forest was a very strong baseline in this other this is a comparison. So maybe we only want to try out a couple of classifiers that work well in many cases. And maybe we also don't need very complicated pipelines that are arbitrary. Maybe we know which kind of pipelines work well, and we can exploit that better. Also, even if we have automatic machine learning, that doesn't really solve all problems, because a lot of problems or a lot of tasks require us to understand the model that comes out. If we build a very complex, automatically tuned neural network or genetic programming generated pipeline, that might not be interpretable in the end. So many of the algorithms also just combine many or an ensemble good algorithms together. So you could run one of these like auto SKlearn, and this will actually find the top best, I think, 5 performing models and just average their predictions. This will make the model better. But this is completely impossible to understand. So there's some trade-off between getting a very good model and getting a very simple model. One criticism that I also heard often is that this makes machine learning too easy, and people don't need to understand it and will sort of abuse the results, or will get into trouble for not having a proper setup. I actually heard this already for SKlearn. People told me SKlearn makes machine learning too easy, that's dangerous. And I think there's no such thing as too easy to use. And I'm very happy that people think that we made machine learning too easy. I don't think it's the case yet. But I think it's important that people understand what they're doing when they're applying machine learning, that they know the right protocols, how to evaluate a model, and what are the implications of a machine learning model in production. But I actually think that if we automate things more, we can have more built-in safety mechanisms to make sure that people do the right thing. All right, so I gave you a link to download the slides. There are some cool papers that I listed. The top one is a survey paper that I really highly recommend. The second one is about robust search for hyperparameter optimization. I didn't have time to talk about hyperband, which is also in there somewhere. Just check out these links. I'll put the link to download is in the chat at the very top. I'll also post it again. So here, the link is here on the slide at the top right. Yeah, also, so as long as there's no automation, I also wrote this book, which tries to make machine learning more simple. The idea of my book is that basically tries to convey the ideas behind machine learning and best practices with very little math. There's a lot of books that are very heavy on math that are very good at explaining the theory. Here in my book, I'm trying to sort of give a more practical approach, and I hope it helps people. Okay, so the question is, how does the machine learning-based approach of meta learning compare with Bayesian optimization? They are not basically alternatives. They're usually used together. So you need to use the Bayesian optimization framework to build the data set to learn the meta learning, because you need some good parameter setting and good pipelines before you can learn the meta model. And then again, you can, once the ML-based system gives you a recommendation, this could be good, but people have found that if they then use this and run Bayesian optimization again, that the results are better. So this is sort of a trade-off between getting a result fast and getting a better result. So you can just get the result that was predicted by the machine learning model. But then if you have more time, you can run the Bayesian optimization again with that as a starting point. Or you could think about even better ways. There's papers how to better incorporate prior knowledge from Bayesian optimization into from the optimization of different data sets into the new. So basically, you can do both of these very integrated. There's a cool paper about multitask Bayesian optimization that does that, for example. Check out the review paper. The review paper that is on the top of the slide has a lot of good links. GA is genetic algorithms, and what's PSO? Particle swarm optimizations. So these optimization problems are all global optimization problems, which means they're all NP hard. So provably, nothing can work. People found that Bayesian optimization is a little bit better than randomized search. And in some cases, genetic algorithms and particle swarm optimization can also be better, but it depends a lot on the formulation. Particle swarm optimization and genetic algorithms, they're like families of algorithms, and you can, it depends a lot on what you do. I haven't seen a very good comparison between these approaches and the Bayesian optimization approaches. Maybe they are in the optimization literature. I would be interested if you find anything. So the teapot that I mentioned uses genetic algorithms, but it also has quite a different approach from the other packages that I mentioned. So you can't really compare them apples to apples. It would be interesting to do a more apples to apples comparison of these two with the Bayesian optimization. But in the end, they're all sort of heuristics for an NP-hard problem. So it's kind of tricky. I guess people like to do Bayesian optimization because they can at least do some. I think it's somewhat easier today to say some things. If the function you're actually modeling can be expressed by the GP, then you can say things about the GP. So it's somewhat easier to do some theory. That doesn't necessarily mean it's helpful theory. I don't know. Yeah, the link that I sent you has the slides. It also has slides with notes. So let me give you the. Well, you can find there's a PDF called Automatic Machine Learning with the best. Thank you everybody for listening, and hope you enjoyed the talk. Have a fun conference. Bye-bye.